What's up, everyone? Josh here. You are about to listen to an episode featuring Isaiah Taylor, founder and CEO of Valar Atomics, a company dead set on building safe and modular nuclear reactors to solve the single most important resource problem in the world, energy. Isaiah's nuclear roots run deep, with his great-grandfather being in the Manhattan Project and Isaiah himself attempting to split the atom all on his own all these decades later. And get this, they did it all both at the age of 24. And speaking of splitting the atom, since this episode was originally recorded, Isaiah and the Valor team did just that, achieving a milestone called cold criticality, which occurs when uranium, the isotope they use as nuclear fuel, it achieves a self-sustaining reaction. It's the first venture-backed company ever in the world to split the atom and do this. It's incredible. This was an episode that David and I recorded early on in Limitless's history, and since then, so many more new people have joined us, and we wanted to enjoy Thanksgiving with our family. So we figured it would be a perfect time to resurface this gem of an episode. And when asking Isaiah to come on, we were hoping to create the canonical energy episode as to why it matters so much for everything we do. And after listening back, it's still holding strong. And I hope that it will also leave you feeling inspired the same way that it did for me. Isaiah is a total badass. If you're listening to this, I highly advise switching over to YouTube or Spotify because he is recording literally right in front of his nuclear reactor. It is so cool. It's an amazing episode. And if you enjoy it, or you have a friend that you think would be interested, please share it with them. It's the best way that we can grow. And we're so appreciative of everyone who was listening to the first version of this and who is listening to the new version of it right now, because it has been an incredible journey. If you can support us in any way by sharing the episode, liking, subscribing on whatever platform you're listening on, leave a nice review if you enjoyed. But without further ado, let's get into this amazing category-defining episode with Isaiah Taylor. I really hope you enjoyed this as much as I did. Why is energy the most important resource in the world?
I would actually argue that over time, energy is the only resource in the world. If you think about what we're all doing as humans, we are creating entropy as we go throughout the universe, and almost anything else that you could come up with, I would argue anything else you can come up with, essentially consumes energy, right? So when we talk about resources, natural resources, we're trying to find things in the ground. But there's a lot of stuff in the ground. And not only is there a lot of stuff in the ground, there's stuff on other planets and in asteroids. And the universe is fundamentally limitless as far as we know. The actual limiting factor in all of these things is how much energy do you have to transform the world around you into what you want? And that's the only irreversible thing, right? If you use copper in an electric car, you can always use that copper again, right? But the energy in that electric car will never be used again. Right, you've created entropy, and that's fundamental. So I actually view energy as like the only cost in the universe, and it's why I focus on it.
I love that. So we are focused on getting a lot of energy. We are energy constrained. I'm curious what you think. What does having an abundance of this energy look like? If we do achieve this goal of getting energy cost to near zero, what becomes newly possible? What does the world look like when we actually solve the energy problem?
So let me put it in terms of what the world looks like now, and that might help us extrapolate a little bit, right? So the sort of like history of what the world looks like in society is essentially three pillars getting better over time. Okay, so the three pillars of any product, any physical good, are essentially energy, intelligence, and dexterity, right? So these three ingredients that you need to make any physical good. Let's take, an iPhone, right? So this iPhone is made of energy, intelligence, and dexterity, right? So it's the intelligence of the people at Apple who knew how to put it together. It's the dexterity of the machines and this, massive CNC fleets and Foxconn and, the physical manipulation of matter that went into putting it together. And then finally, it's the energy to run those machines, to run the servers that are running CAD, even the energy to fuel the designer's brains as they eat food, and they go throughout their days. So every single thing is made of energy, intelligence, and dexterity. And what's interesting right now is that we're getting clear abundance in the intelligence and dexterity part, right? So AI, hitting an inflection really means that intelligence is becoming somewhat default free. Dexterity will also become default free as we get more and more robotics. And so what does the world look like when we have abundant energy? It's essentially fueling those things in an inflected manner, which means everything is free. What does it mean when everything's free? Well, it means that like the material world is more subject to your imagination, right? It's more limited by what can you imagine. Now we're talking like, somewhat far in the future here, but it might be closer than people think it might, think it is today. because we're so used to a world that's constrained, heavily constrained on intelligence primarily. The entire physical world around us has been traditionally constrained on the intelligence of smart people trying to figure out how to translate what's in our imaginations into the physical world. We might imagine an airplane, but then the translation of that airplane into something that can actually fly takes an enormous amount of brain power of thousands of smart people and then a lot of dexterity to manipulate the world. And as intelligence becomes free, it actually just becomes a function of energy. So your ability to get an airplane out of your head becomes how much energy do you have, right? This is a world in which, there are lots and lots of robots, which are robots which build other robots, which build other robots, robots which mine materials, which build robots, which mine materials. And at the end of the day, energy is the input. So what does the world look like when we have abundant energy? I mean, I think it looks like a world of imagination, right? A world of thinking of amazing things in your mind and watching them happen. Now, you can imagine that on planet Earth, that might become a little bit crowded, right? We'll probably have a lot more things running around and planes flying around if we're, subject to imagination. And this is where I think space exploration becomes very, very interesting. And, we suddenly reach out and find more places for us to have imagination, but we use the space around us, like the physical space around us, as somewhat of a canvas on which our minds are imagining and discovering and putting things on that canvas. I'm very excited about that. I think it's going to be a lot of fun.
I think we definitely share that enthusiasm with you. And I love this term that I've heard a lot being thrown around, which is just too cheap to meter, is what happens when that energy becomes too cheap to meter. I think that's the basis of a lot of this show, is what are the downstream effects, what are the second order effects of all of these unlocks happening as a result of energy that's too cheap to meter. So I want to take a step back for a second and just kind of introduce who you are. Isaiah, for the listeners, has a very interesting story. Most people drop out of college and they're like, oh yeah, I showed them, I'm a college dropout. Isaiah, if I'm correct, I believe you actually left high school and then you taught yourself to code and now you're sitting here. And for the listeners at home who aren't listening, Isaiah's sitting in front of a nuclear reactor, in front of their product, in front of hopefully what is the future of energy. So there's this quote that I love from Steve Jobs. It's like, you can't connect the dots looking forward, but you can connect them looking backwards and you have to trust that they'll work out. In your case, it is very clear to me that they worked out. So can you just kind of explain to me how you wound up sitting here in front of this reactor that you built?
Yeah, it's an interesting story. So yeah, you're absolutely right. I dropped out of high school. I actually did attend 3 months of college. I think it was around 3 months. I attended a small liberal arts school for a couple of months while I was working 80-hour weeks doing software engineering. Didn't last very long. I was curious to read a lot of literature, and I've always been interested in language. And I kind of realized a few months into it, like I cared a lot more about the work that I was doing than spending my time in a classroom. A lot of my time in the classroom was spent like sitting on my laptop coding. I was like, okay, I can really only do one of these things well. So, education has always been something that's like a fascinating thing to me and that I want to do more of. But I also am on a mission and I have to fulfill the mission, and so that consumes a lot of my time and energy. But how did we get here? How did we get to Ward Zero behind me, sitting in front of this amazing machine that the team has built? It's essentially been a journey of self-learning, right? So how does anybody learn? Well, they read, right? They read and they talk to people. If you go to school and you learn nuclear physics, you read, you talk to people, you do math, right? That's essentially what you're doing. And it turns out that like if you are wildly curious about something, that you can do that on your own as well. Now you have to be curious about it. I caution people because, sometimes people they see, oh, wow, you dropped out of high school, you dropped out of college, it's super cool. And I actually recommend that people don't do that unless they are overwhelmingly curious about something to the extent that it's going to drive them to try to understand it every single day, right? If you don't wake up like burning with curiosity about a certain thing that you're going to spend your life learning about and building, you should probably go to school, because the nice thing about school is that it pushes you to learn things that you otherwise might not have spent the time to do, right? But for those people that have an itch in their head that cannot be scratched anyway, except waking up every single day and working on it, you will probably find easier and more efficient ways to access that information and start actually building than going to school. And so that's what I did. I've been really thinking about this business for about 10, 11 years, since I was around 14 or 15. I have some family history in nuclear energy that motivated me to go and learn about it. And so that's kind of what I did.
And I want people to also note that you did this in the pre-AI age where you actually had to go and read books and teach yourself things without all of the additional leverage that we have today.
That's actually such a great point. And if I had had access to ChatGPT when I was like 14 or 15, that would have been phenomenal. I'm so excited for the generation of students that are growing up right now who can like sit on ChatGPT for hours and hours, and it's like having a professor talking to you, which is amazing. But yeah, I did this back when it was mostly actually trying to read PDFs from the Department of Energy and the AEC in the 1960s. So I'm at least grew up in the digital era where you could find these PDFs online, which I'm grateful for.
It's pretty clear, Isaiah, that nuclear is your answer, the answer that makes sense to you. Maybe you can walk us through that train of thought as to like why you are just pilled by nuclear specifically, because there's other ways to produce energy. Solar, I still feel like has like a lot of juice left to squeeze in that whole industry. You could have gone and solved the solar problem, but you chose nuclear. Maybe you can just walk us through that choice.
I obviously had a bias toward nuclear. My great grandfather was on the Manhattan Project. I've grown up thinking about it, but I would like to believe I was very objective. And one of the reasons is that I became anti-nuclear pilled when I was in middle school and early high school, because having studied the physics of it and having studied the engineering of it, I thought it was the most amazing thing in the world. And then I started looking around at the market and the deployment, and I realized that the nuclear industry in the West is dead, right? It's completely shuttered. It's gone. It's not doing anything. And in the journey of trying to understand why, I actually became anti-nuclear pilled, and I was like, well, this is an amazing technology, but humanity is not ready for it, and it's not happening, and there's these complexities to it which make it impossible. And so then I backed up and I said, well, I know that over the next 100 years, a society is going to figure out abundant energy, and we don't know which one, right? But one of them is going to, and the one that figures out abundant energy is going to have an inflectionary moment that takes them, stratospheric. And I would like that to be us. I would like us to be the ones that figure that out. And so I actually, backed all the way up to the drawing board and I said, what is the best form of energy we could unlock today? And I believe I actually started with a very blank neutral slate, even a little bit, biased against fission, maybe for personal reasons that I, was maybe even salty about it. I was like, man, it sucks that the nuclear, it's such a cool technology that I have history in, but like it just didn't work. So what is the best form of energy? And that drove me to every form of energy generation. I really started from first principles and looked at how have humans gotten energy in the past. What are some theoretical ways to get them in the future? I looked at solar. I looked at wind, which is a proxy for solar. I looked at hydrocarbons. Geothermal was really interesting. I looked at fission, fusion, all across the board. And at the end of the day, I came to a couple of fundamental conclusions. So if you want to make cheap energy, you're going to have a machine that does it. Right. So there's going to be a machine that's a box, and you build the box and energy comes out of it. Right. So like that's the fundamental thing that we're talking about here. What are the properties of that box? What do you want that box to be like? Well, ideally, you want the box to be small per power. Right. So the box is just not that big versus the power that it makes. OK, so then and the reason that's important, by the way, is like at scale, things generally cost how big they are. All right, that's a little bit of a confusing sentence, so I'll say it again. At scale, things generally cost their size. Okay, so a big thing costs more than a small thing. Okay, a 747 costs more than an iPhone. And that's a pretty fundamental law. It's hard to break that law. You see deviations in things of similar sizes for another reason, and that other reason is rate of production, right? So there's sort of like two fundamental factors in how much things cost. How big they are, how many of them you make. Okay, so but the most fundamental one is how big is it? So an ideal energy machine is quite small and makes a lot of power. So then you back up and you say, well, okay, well, what drives the size of an energy machine across all of these different types of energy generation? You have geothermal, you have solar, you have wind, pulling hydrocarbons out of the ground, nuclear, fusion, all these different things. And what I did is, you might laugh at this a little bit, but I looked at all of the different energy generating machines out there and I said, how big are they? And again, it's not total size, but it's how big are they versus the power that they make. All right, so what we're talking about here is power density. So power density is essentially per cubic meter of machine, how much energy does that thing make? And the answer might surprise you. I'll turn it to you. What do you think is the most power dense energy producing machine?
Machine, like a physical contraption, a physical gadget that humans make.
Yep, physical gadget that humans make, or even that they theoretically could make, right? But that makes energy.
I mean, I feel like I'm just not having high context enough to answer this, but like, I don't know, a dam comes to mind. It's relatively small in the grand scheme of things versus like a field array of solar panels. That's my first intuitive answer. I don't know. Josh, what do you think?
Well, you mentioned the atomic bomb. I'm thinking, well, that seems like it generates a lot of energy. And maybe not
okay.
a machine, but but probably a pretty high density of energy.
We can't really use that energy, though.
Does that count?
We're doing some really, really good exploration here. I really like it. So hydro is not power dense, unfortunately. Hydroelectric dams are freaking enormous. They're gigantic.
Yeah, they're large, yeah.
The Three Gorges Dam in China is the largest concrete structure ever built by humans on Earth.
All right.
Now, it also makes a lot of energy.
Test.
But if you actually do the cubic meters to power output, dams are actually pretty bad. The answer today is actually a jet engine, actually a rocket engine. So a hydrocarbon engine is actually the most power dense thing that we've built yet, right? So if you actually look at a Raptor engine, that thing is like I haven't done the exact math. It might be in the gigawatts per cubic meter, right? So just insane energy density. Now, the problem is hydrocarbons themselves are kind of large, right? So like the actual mass of the fuel, you have to include in that calculation. And then you have to also include in the calculation the machinery that produces the fuel, the machinery that finds the fuel, that drills for it, that refines for it, that transports it, that stores it, puts it in the tank. So once you do all that math, even though a rocket engine or a jet engine is the most energy dense thing we built yet, the apparatus to source the hydrocarbons is actually, large. So
high baggage.
High baggage and just more physical machinery, right? It adds to the total, cubic meters per output power. And again, that adds to cost, right? Cubic meterage of machinery adds to cost. And so now the atomic bomb is actually the right answer, right? So if you actually think about what produces a ton of energy in a very small box, an atom bomb or a hydrogen bomb is that answer, right? That you have put an enormous amount of energy into a very, very tiny frame. Now, obviously, the second thing you said was, well, you can't use that energy, right?
It's not productive energy, yeah.
Yeah, it's too much to be productive. But what this tells you is that fission, and fusion, but we'll talk about that in a second. Fission is actually as close as we've figured out how to get so far to this like almost infinite power source in a box of an abstract size, right? And it turns out for fission that the size of the box is not super correlated with the power output, right? So like the reason that we make fusion machines or fission machines of a certain size honestly has more to do with safety than it has to do with like total power that you can get out of the box, right? The reason that we make things bigger or smaller in the fission world has to do with how safe we want to make them, right? Because you take this to the fundamental limit and, you have a bomb, right? Which is an enormous amount of energy in a very small box, but it's unsafe. And then you go the exact opposite direction, which would be something like the machine behind me, which is very, very safe and it's much lower power density. So this is actually the key to why I believe that fission is the answer for the future. And it's that the constraints around how big that box is really has to do with our ability to engineer it to be safe, right? It's actually not constrained by physics. You can make a nearly infinite energy producing box of almost any size with nuclear fission beyond a certain minimum. There's sort of a minimum size, but around that minimum size, like you can make a box that makes the power of the entire world. And then everything from that point to practicality is a matter of essentially safety engineering. So what this means, and by the way, like the fundamental reasons for this is that uranium itself is just unbelievably energy dense, right? So the kilowatt hours per kilogram on uranium is about 23 million kilowatt hours per kilogram versus, I'm going to get this number wrong, but I think it's somewhere around 40 or 50 kilowatt hours per kilogram in oil and gas, right? In a hydrocarbon fuel. And so you have literally millions of times more energy density in fission. Now, take this to like something like solar, right? What's the power density of solar? Another way you can think about this is here's a trick question: what's bigger, a nuclear reactor or a solar panel?
I would guess solar by a couple orders of magnitude.
Yeah.
Yeah, so it's a trick question because you're like, well, a solar panel's this big, and a nuclear reactor is that big, so clearly the nuclear reactor is bigger. But it's actually not true. The solar panel is much bigger, right, per power output. And the answer is a couple orders of magnitude, maybe 3 orders of magnitude. It's hard to predict in the limit, but today at least, solar is about 3 orders of magnitude bigger in terms of physical mass than nuclear. So if our North Star is that an energy machine ought to be small because small things are cheap, nuclear is the solution, right? So this was sort of my conclusion on all of this, like first principles thinking and research is essentially that fission will create the cheapest energy on Earth if we can figure out how to do it safely, and we can figure out how to do it legally and in a way that the public, will be happy with. Because even if you have a safe machine and the public thinks it's not a safe machine, you still haven't really solved the fundamental problem, at least in a short time frame. So the second conclusion that I had, and this is really what led to starting Valor, is that if you really want to make the cheapest energy on Earth, you're going to do nuclear fission, but you're going to do it pretty differently than how it's been done before. And specifically, you want to do it kind of in the middle of nowhere, where you have sort of a safe operating place for fission, out in the desert, out in the middle of nowhere, with as many safety constraints as you want to put around that, as much security as you want to put around that. And you can simply build many, many nuclear reactors because, again, there's 2 governing principles in how much a thing costs. How big is it and how many you make? So we know that fission wins the smallness thing, right? Very small machine makes a ton of power. The second is how many you make. And so these are the 2 fundamental, decisions that went into starting this company, is that we're going to make fission reactors because they're small, and we're going to make a lot of them because making many of a thing makes it very cheap. And so that's essentially what we're doing here. We're making many, many nuclear reactors out in the middle of nowhere. They're fission reactors, so they're very power dense, and we're going to make the cheapest energy in the world.
I feel inside of your answer, I feel like there's just a lot of work being done with the idea that there's just not a lot of like extra baggage going around the production of energy. So we could go and we could talk about building a dam or setting up arrays of solar panels or wind farms. And I think you would just like dismantle each one of those things, talking about the supply chains that are required to produce those things, the third-party vendors that are required, the assembly that's required. And I'm getting the intuition here that building a nuclear reactor, what you're doing, there's just a lot fewer moving parts. And It's just a more just like simple environment to produce energy. And so you have less dependencies on, third-party manufacturers. You have just overall less dependencies, generally speaking. And that allows you to, in theory, kind of scale out that operation and scale out energy production, generally speaking.
Yeah, that's absolutely true for a lot of industries. Like, it's absolutely true for oil and gas, right? So it's almost impossible today to completely verticalize an oil and gas company, right? Because the source of your oil continues to shift. And so unless you're in like the continuous real estate business where you are constantly buying new patches of land, exploring them, drilling, pumping oil, moving it to refinery, which you own, refining it, moving it through logistics that you own to the end user site, that's an enormously complicated supply chain to own yourself. Now, what does verticalizing nuclear look like? Well, it looks like having a patch of land where steel comes in and graphite comes in and energy comes out, and a bit of uranium, right? But the uranium part of that is actually shockingly small in terms of mass. Right.
A little uranium goes a long way.
A little bit of uranium goes a hell of a long way. So now, solar, you can make an argument about this as well. You could say that you have this solar plant, which is similarly structured, which has silicon coming in and aluminum coming in, and you have power coming out. Now, the problem with that is just the mass constraint, right? You're going to need a couple orders of magnitude more silicon, more aluminum than I need, steel and graphite and uranium, right? So at the limit, I say I win that fight just in the fact that I need literally 1,000 times less physical material per output power. And, in the limit, things cost how big they are. So, this is sort of the math for solar. Now, fusion is an interesting part of this as well. People will say, well, okay, fusion is even more power dense, right? Because, deuterium versus uranium or tritium, are even more power density per kilogram. The problem with that is that, again, it's more about the properties of the box than it is the properties of the fuel, right? What is, like, let's characterize a fusion box. How good is that thing on the metrics that we talked about, right? An energy box should be small. That's the first most important thing. I would say there's two other sub attributes as well, is that they should be simple and made of common materials, right? Small, simple, common materials. Interestingly, fusion is worse on all three of those than fission, right? So a fusion machine is actually larger per power because it's harder to capture the energy out of it. It's harder to create the conditions for fusion. It's hard to capture the output energy. So the machine itself is actually larger per power than a fission machine. It's lower power density. It's also much more complex, right? And complexity is a factor to cost. And the materials are much less common, right? So you can't make a fusion machine out of steel and carbon, right? Which is essentially what this machine behind us is made out of. And so, like I said, I would like to believe I was objective in this. I did not know what the answer was going to be. I thought it might have been solar. I thought it was, I actually thought geothermal for a while might have been the answer. But when you actually go to how does humanity have civilizational, energy that is 10 times cheaper than it is today, the only answer that I see to that is nuclear fission.
Why do you think that this is ready for society right now? Nuclear as a conversation goes back before I was born, before all of us were born. Yep. It's been around for a while. Why now? What's changed with technology? What's changed with politics or just the world around? How has the environment changed to make the question of right now be relevant?
So I think that we made a trade-off in the 70s and 80s that made us think that energy wasn't that important for a while. And that's one of the fundamental reasons. There's a couple fundamental reasons. So in the 70s and 80s in the West, we essentially became a society that imagined it could be somewhat decoupled from the price of energy. And the essential way that we did that is we exported physical industry to other places, right? So energy really, really matters for physical industry before AI. Now energy matters even for bits, right? But before AI, energy was really, really important to physical industry. And we went through this motion of essentially moving all physical industry to other places. And so it didn't matter to us. It didn't impact us as directly to have more expensive energy. And so I would say there's a period of irrationality in how we thought about energy because we thought it didn't matter. Now, it turns out that you actually really need physical industry as a country, right? A nation needs to be able to build things. And in fact, I would say the fundamental thing that an economy does is building things. But there's the flaw in our thinking came from the fact that there are actually like two things involved in making things. There's the knowing how to make them, and then there's the making them. And we imagined for a period of 30 years or so that we could be the country that knows how to make things, and that other countries could be the ones that do the making. And in the short term, that looks really attractive because you get a ton of alpha on the knowing how to make things. You have rapid growth of valuable intellectual property. It's really easy to capitalize. It's really easy to get started. And, we're like, let's just export the annoying part, which is like the real making, to other places. And that's highly flawed in the long term. It maybe is a good idea for about 10 or 15 years. In the long term, it turns out that your ability to know how to make things has to be coupled with the making of them, right? Because what happens is you forget. You forget how to make things. And if you're not actively making things, you're not learning how to make them better. So the practical, output of this is like, we forgot how to make cars, right? Like we started exporting car production to other places, and Japan got really good at it. China got really good at it. And really only one company in the United States sort of like was like, maybe we should remember how to make cars and make those again. And, that'd be Tesla. And this happened across, so many different industries, right? The reason that Silicon Valley is called Silicon Valley is that we used to make silicon there. We used to make chips. And then we exported them, somewhere else for the actual production because we didn't want the effluent and the waste from that. And now, guess what? We don't know how to make chips anymore, right? So this is very short-term thinking. You actually have to be involved in the making in order to be educated on how to do the making.
I'm reading a book about this same effect with Apple's iPhones, where they exported all the manufacturing to China, and that it ended up actually just being an incubator for Chinese phone production. And so Huawei and all of these other Apple competitors all came out of China. And now actually only China knows how to make phones, including Apple iPhones.
Correct.
And so like Apple is now realizing that they incubated the whole entire Chinese manufacturing thing, which is now the centerpiece of a lot of geopolitical debate right now.
Exactly. It's a short-term trade. It's something that finance people do because they want to make, a little bit of a better return in a 10 to 15 year period. And then after that, you realize that you exported the ability to actually know how to make things, because the physical world is a real place, right? You can't actually model everything perfectly. You have to actually see how the steel behaves in practice. You have to see how the machine behaves in practice. And so, yeah, I think it's. I actually don't even remember this question started. Now you've gotten me on a separate soapbox that I care a lot about. But you can't decouple those things for too long. Oh, we were asking why fission now.
You're right.
This is one of those reasons, right? So we've had a return of rationality about making things in the physical world is one thing, right? So we suddenly realized like it's actually probably important that we know how to make steel, right? It's actually important that we know how to manufacture things. And when you do that, you realize that energy price is really, really important. Right? The reason that China dominates global aluminum is because they have 3 to 4 cents a kilowatt hour coal energy, right? They can make electricity at 3 to 4 cents a kilowatt hour and electrolyze bauxite. And that means they dominate aluminum. That also means they dominate gallium and germanium as well, which are really, really important to producing chips because that's downstream of bauxite electrolysis, right? And so this return to rationality drives us back to understanding that energy price in a society is really, really important. It's a strategic thing that a country has to have. The second thing that's happening is AI, right? So all the bits people suddenly woke up and realized like, okay, we actually need energy to even do our bits now. Because it used to be that a data center, the electricity price in a data center just didn't matter that much because you weren't using that much compute to send emails around. Now we're using an enormous amount of compute every day just to do our basic stuff because we want to use ChatGPT for everything. So that's the other thing. And so both of these things are just, this return of rationality to the West to say, we need cheap energy. And you look around and you do the same logic that I did and you realize nuclear is cheap energy. And by the way, you don't have to believe anything that I've said, in theory about why nuclear will be cheap. You can actually just look at the past, right? So in the early 1970s, before 3 Mile Island in the United States, nuclear fission not only was the cheapest energy source, it remains the cheapest energy that humanity has ever experienced, right? So I'm going to say that again. In the early 1970s, the energy that we were getting out of nuclear reactors at that time remains the cheapest energy that humanity has ever experienced. And this is adjusting for inflation, right? I'm not talking about nominal $1970. I'm talking about $20, we were getting around 3 to 3.5 cents per kilowatt hour energy out of nuclear reactors, right? Now, we've the cheapest energy you can get in the United States today is somewhere around 5 to 6 cents per kilowatt hour. It's a little bit difficult to calculate because of subsidies, but that's about as good as you can get. So we're about double, right, the energy that we were getting in the early 70s, even when adjusting for inflation.
50 years ago.
50 years ago, yeah.
Mm-hmm.
And energy should always move the opposite direction, right? 50 years later, you should have 10 times cheaper energy than you did before. That was the trend up until the 1970s, and it was reversed. So I think there's this massive return to rationality on energy price, which naturally leads you to the conclusion of fission. The other interesting thing is that I think that nuclear has had really bad marketing, right? It's had this intense scariness attached to it, which I think is very unjustified because nuclear is the safest source of energy on Earth. If you look at power generated versus human death toll, nuclear is the safest form of energy on Earth. It's even safer than solar, by the way. And we can talk about why that is in a second. But one of the interesting things that happened was we had these nuclear incidents in the 70s and 80s. You had Fukushima, you had Chernobyl, and those were wildly misunderstood by the public. If you ask people on the street today, like how many people died in 3 Mile Island, people will say numbers in the hundreds, they'll say numbers in the thousands, some people will say 10,000. 0 people is the answer, by the way. 0 people died in 3 Mile Island. Nobody died. If you ask people
what about second order consequences of like polluted soil, polluted land, downstream effects, anything like that?
13 independent studies after 3 Mile Island that were largely funded by people who wanted to show that the nuclear industry was bad failed to find any environmental or health effects beyond the fence of the 3 Mile Island facility. Not a single study, even funded by enemies of nuclear, failed to find a single negative health effect or environmental effect beyond the fence of 3 Mile Island, right? So Now, this didn't matter in the 70s and 80s. And the reason was because information flow was pretty centralized in the 70s and 80s, right? So if you had the media on board with the narrative and you had Hollywood on board with the narrative, you generally, had a good grip on what people thought about a thing. Now, we've had another nuclear incident since then, and that was Fukushima, right? And Fukushima, most people think was, another death toll of nuclear. I actually take the opposite view. I think that Fukushima was, on net, will prove to be a very positive thing. And the reason is because it was very similar to 3 Mile Island, right? It was 0 people died. There's maybe an argument that you can make that 1 person died, maybe. But it had a very similar impact, right? In terms of public sentiment, people immediately reacted the same way that they did for 3 Mile Island. There was this huge thing. They evacuated tens of thousands of people from the area. They shut down the nuclear industry in Japan for a couple of years. The reason this was different is that this is the information age, right? It happened in 2011. It happened in the age of the internet. And very quickly after this, people started to actually read the data and they realized, wait a minute, nobody died. And, the social impact of actually evacuating tens of thousands of people was orders of magnitude worse than the event itself. And the economic impact and even the death toll impact of shutting down all the nuclear reactors in Japan was, again, orders of magnitude more damaging to the Japanese than the actual event itself. And the fact that this happened in the internet age began to wake people up. And you had a second backlash to that, where the Japanese went back and they said, we made a huge mistake, right? We made a really big mistake by evacuating tens of thousands of people and by shutting down our nuclear industry. And they're beginning to turn all those plants back on. And so I think that these are the two kind of factors that are bringing nuclear fission back today, is that it's the information age, right? Anybody can go and read about Fukushima. Anyone can read about, the Japanese decision to reverse, the impacts of that and to turn plants back on. And then again, just a massive return of rationality to the importance of energy in the Western world.
Yeah, 50 years is such a long time. And you mentioned the world of bits that we largely live in. And for the people that are not familiar, the world of bits is basically the computers, the ones and zeros that kind of run the world. But what we're talking about now is the acceleration of the world of atoms, which is the physical space, the meat space that we occupy right now. And there's definitely this trend that I'm starting to see, and you mentioned, in that people are starting to learn and get excited about this world of atoms. How do we create these physical objects that can break these barriers that have been left behind, like energy 50 years ago? So I'm curious about your take on all of this. You co-founded a company called Valor. I'm curious how you think Valor can solve the nuclear energy problem. What are you building? For the people that are listening, you are sitting in front of what I believe is called Ward Zero. It's your first prototype reactor. So can you just explain to me kind of how you're tackling this problem in the world of atoms, giving us energy through Valor?
Absolutely. So I'll tell you about what we built here and then what we're going to build in the future. So Ward Zero is the object standing behind me. This is what's called a non-nuclear prototype. So essentially what we did is we built a nuclear reactor, but we didn't put uranium in it. Right, so that's kind of how you can understand what's behind us. Built a full nuclear reactor. You could put uranium in this thing with a couple of minor modifications, and it would actually turn on and it would split atoms. Now, we don't do that because essentially the paperwork to actually do that in the United States would take 4 to 5 years, and we don't have 4 to 5 years. We have to do this immediately, right? So build a full reactor, and then what we put in it instead is silicon carbide. Silicon carbide is a great material. It's an extremely high temperature ceramic that's also a great electrical resistor. And so what that means is that we can basically dump about 12 city blocks of Los Angeles power into the core of this reactor, and we can simulate what a nuclear fission reaction would be doing inside that core, which is essentially generating a ton of heat, right? And then what we do is we process that heat in the same way that we would if this were uranium making the heat. So this gives us a very, very high fidelity, real world simulation of what a nuclear reactor would actually do. And the next step is to essentially go rebuild this reactor one-to-one with a couple of lessons that we've learned on how to weld this thing, how to structure that thing, how to seal this thing, but actually put uranium in it and turn it on and split atoms for the first time. So that's the next step for the company. The vision of Valor is to, rather than building these massive nuclear plants that we did over the last 50 years, you had these like gigawatt scale reactors. We believe that small reactors are better in a bunch of ways, that this architecture is also better. This is a fundamentally safer nuclear reactor. It uses graphite instead of water as the moderator, and we can talk about why that's safer. But the plan is to, instead of building, let's say a couple dozen very large reactors, we want to build thousands and thousands of these smaller reactors. Because again, one of the drivers to cost is, there's 2 drivers of any physical good in terms of cost: How big is it? How many you make, right? So we want to make small things that you make a ton of, and that's going to make them really cheap.
Is the idea here that I'll be able to go down to my local Valor store and pick up a nuclear reactor and plug it into my home? Or how does that actually like plug into the grid and start giving me energy?
Yeah, so I would say probably not for a while. Nuclear reactors...
I'm surprised that the answer is reasonably yes at all, to be honest.
I think over time, humanity continues to use nuclear fission more and more and more. It becomes the dominant source of energy in the world. But there's two questions at play. There's like, where does the energy come from? And then how does it get to you, right? And those are two different things. One of the nice things about nuclear fission is that you make a ton of cheap energy in a location, and then you can sort of firewall the nuclearness of that from the end user, right? And the firewall there is that you transport the energy through a medium. And that medium is either electricity or it's also chemical energy, right? And the chemical energy part of that is really interesting. So our nuclear reactors will make both. We'll make electricity. You can get our electricity from a grid, and it should be much cheaper. We'll make electricity for AI data centers, and those data centers will be getting the best power rates in the world. But also we'll make chemical fuels, right? So we'll actually make hydrogen. We'll bond that hydrogen with CO2, and we can actually make a synthetic fuel. We can make diesel, gasoline, jet fuel. And you might get that in any of the places that you get those chemicals today, and those chemicals should be much cheaper. And so essentially, if you think about what we're doing there, we're arbing the physical infrastructure of hydrocarbons as a logistics platform, and we're plugging nuclear into it, right? And why would you do that, by the way? Like, what's the point of that? Well, the point of that is that the think about hydrocarbons for a second as a grid. All right, so we're familiar with like an electrical grid, right? You have a bunch of wires connected and you push electrons through and people get to consume that energy. Hydrocarbons are also a grid. They're a liquid grid, right? They're a network of pipelines and trucks and tanks that move them around. So let me ask you, which one is bigger, right? Which one's moving more energy, the electrical grid or the hydrocarbon grid?
I would imagine the hydrocarbon grid, because that's the whole combustion engine thing. Like, how big is the combustion engine as a concept? I would imagine it's massive.
Here's a crazy stat for you. On the ocean today, there's a bunch of ships, right? And those ships are burning hydrocarbons to propel themselves across the water. The energy being consumed by ships on the ocean today is greater than the entire electrical grid of the world. Just
the ships.
Correct. Just ships burning hydrocarbons are consuming more energy than the entire global electrical grid. Right, so
that is a fun fact.
That is
hydrocarbons.
Unreal.
Hydrocarbons are actually a much larger grid that's more distributed, that's more flexible than the electrical grid today. Right now, there are some downsides to hydrocarbons. Right, one of the big downsides is that you're continuously adding CO2 to the atmosphere. Every year that you use them. Eventually, we want to stop doing that for a bunch of reasons. It's not just climate change; it's also the fact that eventually the CO2 level in the atmosphere becomes too high for after about 600 ppm, your brain function, starts to go down, those sorts of things. So there are lots of reasons why over time that's not sustainable. But if you just think about it as a grid, right? Think about it as just moving energy around. The hydrocarbon grid, I would say, is far better than the electrical grid, and it's far larger. And it has, potential to move, terawatt hours of energy around. Now, if you could fix the CO2 problem, part of that, and only get the logistics part, you would have essentially given yourself the ability to distribute all of the world's energy from only a couple of points, which is great for verticalization. And it's actually quite solvable. The way that you do that is you take the CO2 out of the atmosphere and you build it into a hydrocarbon, allow people to burn it, which puts it back into the atmosphere, and you take it back out, send it out, allow people to burn it, puts it back in, you take it back out, and you've created a closed loop of CO2, right? So you're not adding net new CO2 to the atmosphere every year. You have a fixed rate of CO2 ppm, and you're essentially just using the atmosphere as a transport mechanism to get your ingredients back to you again. Because remember, CO2, it's not carbon that's energetic; it's the structure of the molecule that's energetic. And the nuclear fission is essentially infusing CO2 and water into an energetic form, which is a hydrocarbon, right? You're ejecting the oxygen out of that, and now you have an unoxidized chemical. And I'm sorry, I know I'm getting a little bit chemistry, borked here, but that is essentially what we're planning to do.
Yeah, I'm going to try to ask you this question in a way that you can explain it to normal people, where we don't go too deep in chemistry. But I'm curious about what makes these reactors different than I know the pebble bed reactors are very popular. The Gen 4 reactors that are coming, they're much larger. You mentioned modularity is one part of it, but what are the benefits aside from the small size, aside from that modularity, that you are kind of taking advantage of relative to the size? Is it just size, or is there something else that's also going on behind the scenes or within the reactor that makes it more, I guess, more powerful and more efficient?
So I would actually say that these reactors will be less powerful per size than some of the reactors that have been built before. The reason that we do that is that it makes it safer, right? So one of our beliefs here is like safety is probably the most important driver of cost in nuclear. If you can make a reactor that's 10 times safer, you can actually make it 10 times cheaper because it allows you to do it more often, more quickly, deploy it at scale. So these will actually be a little bit less power dense than traditional light water reactors. But we actually get to manufacture them. We get to make a ton of them, and that makes them cheaper. The really unique thing here is that these reactors are just a lot hotter, right? So the outlet temperature on these reactors will be around 800, 850 degrees Celsius. That's compared to 300, sometimes 350 degrees Celsius in a light water reactor. That unlocks two really important things. So the way that you make energy in a nuclear reactor, traditionally, is that you have a very hot outlet temperature, and then you have ambient air at a certain temperature as well. And you can extract energy from the difference between those two temperatures, right? And this is called Carnot efficiency, right? So you have a T hot and a T cold, and the difference between those temperatures governs the maximum amount of energy they can get out of that. For most plants around the world, this is 20 to 30%, right, of the total energy that you can get out of that. In a hydrocarbon engine, which works a similar way, you can push, into the mid 30s in, very efficient nat gas combined cycle generators. You can push 50% total efficiency. But this is all limited by the basic physics of the difference between your hot side and your cold side. The way to increase that diff and the way to increase the efficiency is essentially just to make the difference larger, right? The larger the difference between the cold side and the hot side, the greater efficiency you can get out of that. And it turns out that at 850 C, you can actually get really efficient at producing electricity, right? So we'll be significantly more efficient at producing electricity than a traditional nuclear reactor. Now, the other really interesting thing that gets unlocked here by doing high temperatures is actually direct production of hydrogen, right? So ideally, right, hydrogen is a chemical energy, right? Pure hydrogen, because it's deoxidized, and the fact that we have oxygen in the atmosphere means that it's chemical potential energy. If you take that hydrogen and you combine it with the atmosphere, you get water and you get a ton of energy, right? So in theory, a really good thing to do with a nuclear reactor is to seed that process, right? You get some water, you combine it with reactor energy, and you get free hydrogen. And now that's a very valuable thing that you can go and sell. You can combine it with CO2 to make a hydrocarbon. You can do a bunch of things with it. Now, the way in the past that people have thought about nuclear to hydrogen, is to start with electricity, right? So have a nuclear reactor that spins a turbine, makes electricity, run the electricity through an electrolyzer, right? That electrolyzes water, and then you get hydrogen out of it. The problem with this is that you get two efficiency hits, right? So you get the efficiency hit of making electricity, right? Which, as we know, could be a 60%, 70% hit to your efficiency. You lose a ton of that energy just making the electricity. Then you have the efficiency hit of running it through an electrolyzer, right? And that electrolyzer also has an efficiency, related to it as well, and you're losing a lot of that energy. So by the time you've gone from uranium fission in a core to chemical potential hydrogen, you've lost a ton of energy in that process. The other thing is you've added a lot of physical machinery, right? So you've added a turbine and a generator and an electrolyzer. And again, you want to make machines as small as possible and as simple as possible. An interesting alternate to this is that you just use heat to split water, right? So any chemical will actually decompose. It'll break down at a certain temperature, right? So at a certain temperature, every chemical compound will decompose. And so in theory, you can essentially just get water hot enough from a nuclear reactor to get free hydrogen out of it. Now, in practicality, if you catalyze it properly, that temperature is somewhere around 1600 to 1800 degrees Celsius. That's too hot for us today. Someday we'll have reactors that run that hot. Too hot for us today. But what you can do is you can run that water through a couple of chemical cycles and transform them into another chemical that has a much lower decomposition temperature. So what I'm talking about here is something called the sulfur iodine cycle. The sulfur iodine cycle is a chemical cycle that takes water, makes two other acids out of that water, and then you use heat to decompose those acids, and you get hydrogen out of that, and then you recycle the ingredients. So sulfur and iodine, if you combine water with sulfur dioxide and iodine, you get two acids out of that. You get a hydriodic acid and sulfuric acid, and you can actually decompose those two acids just below the output temperature of this reactor, right? So you can do it around 750 to 800 degrees Celsius, and they will just thermally break down, and you get the free hydrogen out of that. So what are we left with? Well, you don't need a turbine, right? Because we're not making electricity. You don't need a generator, and you don't need an electrolyzer. Instead, you just need a couple of tanks of chemicals, right? And need a good heat exchanger to do that thermal decomposition. So we see this as an incredible way to, at a much higher efficiency, where you're not limited by the Carnot cycle and you're not limited by the efficiency of an electrolyzer, to essentially just take reactor heat with very minimal moving parts and just a couple of tanks of chemicals and make hydrogen. And we think it'll be the cheapest hydrogen in the world. Sorry, you told me to say that without chemistry, and then there's a ton of chemistry.
No, there was a lot of chemistry and like matter. That was in a contrast of bits versus atoms. That was heavy on the atoms side of things.
Yep,
and,
for sure.
Maybe you could just like extrapolate, like when we're talking about atoms and moving atoms and manipulating atoms to produce the things that we want. The conversation starts with a lot of the stuff that you just said. First, it starts with getting the energy, producing the energy in order to manipulate atoms. Josh brought up this contrast of like for the last 30 years since the rise of the internet, the rise of Silicon Valley, humanity has really been heavily invested into bits. Like, how do we make the bits in the right order, the ones and zeros in the right order to produce value? And like atoms has lagged in contrast to bits over the rise of the internet. But you are getting really excited about atoms. Maybe you can you get me and Josh and also our listeners, get them excited about atoms. Like once we unlock having the right atoms in the right order to unlock energy, how does the world of atoms get easier to change, easier to flip a bit? Like how do we get it getting flipping atoms easy as flipping bits downstream of all of this? Just get us excited about atoms.
So I'm actually going to flip it around for you a little bit and say,
sure.
Everyone has always been excited about atoms. Like atoms is actually what we have all cared about for the last 50 years, but we also care about money, right? And what's been true over the last like 30 to 40 years is like, well, first of all, the reason we care about money is generally because of atoms. Like what do people do once they get money from, let's say, starting a SaaS company and becoming a billionaire? Well, they spend that money on atoms, right? They start to have a private chef, which makes them delicious food. They get a private jet, which like flies them around wherever they want to go. They get a beautiful house. They get a boat, right? So I would actually argue like the world of atoms has always been the thing that is very interesting to people. Now, the second thing is that there's this intellectual side that's also very interesting to people, which is like the right way to order bits, right? And that is like a captivating question in the mind that has driven a generation of entrepreneurs and a generation of innovators and engineers. But I think that's mostly just been driven by the fact that the world of bits was really the only place you could be intellectually curious, right? If you're a intellectually curious person and you're an engineer and you have the option before you life starts when you're in high school, right? So like when you're in high school and the options in front of you are opening a laptop and creating something, right? By the end of the day, right? By the end of the day, as a 17-year-old with a laptop, you can have created something that's functional and maybe even makes you some money. And a couple years later, you could be making a lot of money. And in 5 years, you could be a millionaire, right? Like the world of bits was the place that happened. So I think that our obsession with bits is actually more an obsession with innovation. It's an obsession with discovery and with engineering. And the world of bits was the only place you could really do that. So then we have to back up and say, like, why was bits the only place you could do that? Well, there's two reasons. Like, one is the simple like political answer, right? Which is like it became very hard to do things in the world of atoms in the West. We added an enormous amount of federal regulation over everything that moves, and we didn't do that in bits, right? And so a 17-year-old could open a laptop and create something with almost no interaction with regulation, whereas just trying to make a sample rocket, you're wondering like, oh, am I south of some sort of like regulation here that says that I can't have, this chemical in this room and that sort of thing. And so there's just a very quick, easy path to being an engineer, to being an innovator, to being somebody who's intellectually curious with bits. The other thing, though, is that it's the second thing we talked about, where there is a fundamental limitation in the world of atoms that hasn't existed in bits in terms of like cycle time, right? Like, so the fact that if you're sitting in front of a laptop, you can have a piece of software at the end of the day that's doing something cool. Whereas, if you have a physical thing in your mind, it maybe takes a couple of weeks, right? I think that's also changing. And that's what I'm really, really excited about, right? The things that we talked about before, you have energy, intelligence, and dexterity. As intelligence and dexterity get cheaper and energy gets cheaper, I believe that we will start to play with matter in the same way that we play with bits, right? Life starts in high school, okay? It starts where you play. The reason that we have so many incredible software engineers and so much software is that people play with computers when they are in high school, right? And they're in literally play, right? We're playing video games. A lot of software engineers that I know got into software because they were playing video games, and it gave them this like love of computers. And then they started modding the software, and they wanted it to do cooler things. And that taught them software engineering because they want to make an extension to Minecraft, something like that. And I think that we're going to start playing with atoms. What would playing with atoms look like? Well, it would look like talking to an AI that runs a CNC machine or runs a 3D printer. And you actually can start to get these cycle times again. You can maybe by the end of the day be holding the thing that you thought about. And then the next day you tweak it and you make it better. You could be holding the physical object that you were thinking about. I don't think I need to convince people that that's more exciting than making software, right? Like, you imagine, a drone that can fly you around, right? And within a couple of days, you're sitting on it and it's in the air, right? Like, that's the future that I would like to see, and that I think happens in the next 10 to 20 years as dexterity gets cheaper, as intelligence gets cheaper. I don't think I will have to convince many people to be tinkering with the real world once it becomes possible to do that again.
Yeah, that sounds right. And it feels like the world of atoms, as that accelerates, will be even more accessible and more, I guess, quality of life improving for the average person than the world of bits. I feel like with the world of bits, and correct me where I'm wrong, but a lot of times you are extracting value from software, or maybe you're injecting yourself into social media. You're just kind of reading and writing with this thing, but it doesn't extrapolate out too much into the real world. So when we do have this accessibility, I think about myself and where I could use an abundance of energy. My car, for example, it costs 20 something cents per kilowatt. If we get that down to free, it becomes much easier to get around. But even things where we're building humanoid robots and these things can probably be more cost effective. I'm curious kind of if you have any fun or interesting examples to get people excited about what it actually looks like for the average person. Like how's my day actually improved as we get this abundance of energy that's much cheaper?
Yeah, absolutely. I mean, here's just a really like everyday person example. The reason that your dishwasher sucks is because of energy regulation, right? The reason that you can't just like throw an entire plate of food into the dishwasher without having to do any wiping. Like, all right, when you're done eating food, you should basically just pick up the plate in front of you and like throw it to a machine. And the machine does the rest, right? And like the next time you're ready to eat food, you like pick up a plate, you put food on it, and then you like throw it back to the machine. That's how this should work. And the only reason that it doesn't work that way is actually energy regulation. It's called Energy Star. There's a fleet of regulations that we've put around how our appliances use energy that has essentially forced the industry to create these machines around a function of regulation. Why do like dishwashers and washing machines like seem like they don't really get that much better and the user interface doesn't change that much? It's essentially because we're solving for energy regulations, right? So in an energy abundant future, like the machines should just do the annoying stuff for you. We're 50 years from the invention of, maybe probably more than that, of the dishwasher, and it's like not that different of an experience. So I would say like, let's get way more creative. Like what does living in a house look like? Well, it looks like just doing what you enjoy. And, when you're like literally throw it, I think that'd be pretty sick. Like I want to see somebody come up with like a dishwasher of the future where you literally throw it. That would be sick.
That'd make me real happy.
And like all of your clothes, like your dishwasher, your washing machine should not just, first of all, you shouldn't load it. Like what is loading it? That's nonsense. Like I want to throw my clothes at the basket and it just comes back folded. Right, my washing machine should fold my clothes too, and should put them back in the drawer. And that sort of thing is like very, very obvious to me. Maybe that's through humanoids. Maybe that's through just better dishwashers, and the concept of a dishwasher becomes very different. But all of these things are unlocked by energy. Now, something that's very motivating to me, I talked about the dishwashers and the washing machines because that's like an everyman thing, but like I'm also extremely motivated by outer space, right? And there's no formulation where we are man among the stars, man on the moon, man in Mars without abundant energy. And that's what's really, really exciting to me. Energy is essentially the biggest tool that you need to go and make the solar system a fun place to be for humans. It's how you can terraform a planet. It's how you can create habitations. It's how you can create, big floating cities above Venus. And there's lots of mechanical problems to solve in there. But again, there's an extent to which mechanical problems will be solved by intelligence, right? Intelligence and dexterity. And essentially, you just need a lot of energy to do it. That's what I'm really excited about.
So I feel like there's probably these two core pillars that people can get really excited. It's about how this energy affects their everyday life. And we could probably have a full podcast conversation about the interesting new ways that you could design things that we use every day to be improved. But it's also the dreamer vision, where now because we have this new abundant energy unlocked, we can dream about going to the stars and the downstream effects of that. We had Sean McGuire on the show fairly recently, and he was talking about how focusing on something like Mars has downstream effects for people back at home, where in order to get to Mars, we need that nuclear reactor that fits in a suitcase, and we need all these new technologies. So I think, and I'm hopeful based on what you're saying, is that we will get all these downstream effects hopefully fairly soon, or at least directionally we're headed towards that now in the way that we weren't in the past. I'm curious what you think about timelines. When will people start to notice the effects of this cheaper energy? When will we start to have dishwashers that can catch the dishes, or robots that can fold our clothes, and in a way that's kind of accessible for the average person to use?
I think that is entirely limited by entrepreneurs, right? So when we think of like tech today and we think of like startups today, all we're really talking about is like young, crazy people who have some like wild vision of how a dishwasher should actually catch your plate, and then decide to go make that thing a reality. And the fundamental motivation for that is twofold. Like, one, they want to imprint their will on the universe, and they want, every single home to have a dishwasher that catches your dishes. Two, they want to become a billionaire or a centimillionaire or whatever. Becoming a centimillionaire and the possibility of imprinting your will on reality has been mostly impossible in the physical world in the West, right? It's different in other countries in the world, specifically China. But in the West, this has not been a path because of not enough energy, and also because of very stringent regulation that makes it just difficult for innovation to happen and difficult for companies to scale. I think both of those things are heading in the right direction right now, which is that you see tons of entrepreneurs suddenly realizing that you can become a billionaire by making something cool. Impulse Labs is a great example of this, right? Sam is a buddy. He was like, stoves should be 100 times better than they are right now. Right. And that's what he's doing. So I think there will be a ton more people who go out and do things like that. The second side is the regulation side. I think we're seeing a lot of fundamental change in how we think about regulation, especially at the federal level, that will affect that, significantly. But it's gated on people listening to this podcast. Like, it's gated to young people in high school who are like, I have a different vision for what your couch should be. I think the couch should be way sicker than it is right now. And I'm going to become a billionaire doing that.
That's a future that seems really excited, that I can get very pumped about. It feels like the future ahead is actually going to look like the future. When I look out over New York City, it will probably look materially different than over the next decade than it did in the past decade. So that's a future I think a lot of people can get super excited about.
This is a great point, by the way. And in the future, looking like the future is like also why we did this. We have a bunch of people on Twitter. I collect Twitter haters. It's very fun. Who are like, why does your nuclear reactor look like a video game, or like, what's going on here? And like the answer
it reminded me almost like an NVIDIA GPU type thing. It looks very cool.
I tried to make it not look like a GPU. It's very, very hard to make a vertical box not look like a GPU. It's just kind of what they look like. But it is very futuristic. It's Tron, it's Star Trek. And yeah, the reason is absolutely the future should look like the future. And when you're walking into a nuclear reactor that was built in the year 2025, it should not feel like you're at like a hospital switchboard in the 1970s. Right. And that's definitely what we're going for here.
For the podcast listeners that are not watching the video, Isaiah's background is the most sci-fi industrial looking thing. It looks like like you just opened the first level in Doom and you're on Mars. While he was talking, a man in a Segway just zipped on by, going like 20 miles an hour, and it was extremely distracting because it was a little bit surreal just watching this man zipping around this factory floor with a nuclear power reactor.
I didn't realize that. That's great. Sometimes when I'm on calls, people think that this is a fake background until they see a forklift go by, carrying a pallet, and they're like, "Oh, that's real. That's happening."
It's very real. Well, there's one more topic that I wanted to touch on that's very front of mind for us, particularly here. Limitless is how we're powering kind of this AI and the intelligence revolution, and how we're doing these data centers, then kind of how we power the rest of everything. So these are our modular reactors. I understand that you can use them in clusters. You could kind of stack them on top of each other to create data. What I understand also is companies like XAI and companies like OpenAI are kind of energy constrained. And what I'm curious to ask you about is will this technology be capable of powering these data centers, one? And then is it actually powerful enough, or is it modular enough that we could scale that across the country to the average person? So like, will we be able to power data centers? Will we be able to power my neighborhood? How does that kind of distribution of these reactors work as you start to roll them out?
Yeah, so this is, just good business sense at this point. How do you actually go and scale a business? I would love if our reactors in the next 5 years could power every American home. There are business constraints to that, regulatory constraints to that. I think the easiest thing for Valar Atomics to do today is to go help AI achieve all of its goals, right? Help all of the hyperscalers get all of the power that they need to win the AI race, to make sure that the United States of America is the most dominant AI country in the world. That's a massive, massive problem that we're going to solve in the next 5 years. Now, beyond that, yes, I'm very excited about that energy getting into your hands. And I think there are two ways that can happen. The one way is, we go and build, small reactors around the country, right? So we have 4 of these units next to your neighborhood, that sort of thing. Another really interesting way, though, is that we just make the hydrocarbons that the world consumes, right? So if you're going to get on a jet aircraft in about 5 years, I hope that fuel is made by Valar Atomics reactors. And I hope that fuel is about a third the cost that it is today. And because fuel is the largest operating cost of an airline, I hope that your plane ticket is much cheaper, right? And if you're going to be, driving on a bus, or you're going to be driving on a truck, or you're getting goods delivered to your house, from a semi-truck, I hope that all of those things are much, much cheaper because they're buying Valar Atomics fuel, which is a whole lot cheaper than refining oil. And then in the long term, I think absolutely our reactors are powering the grid all around the world.
I'm curious about the global energy mix, kind of how prescient nuclear is relative to others. So we're burning lots of fossil fuels. We have a lot of solar energy. Does the equilibrium eventually balance out to a mix of those three, or do you see a future in which it's actually all just nuclear?
I believe that the power mix in the next, let's say, 50 years is going to become 99-1. 99 nuclear fission, 1%, other things. I think that solar will always have some applicability in remote places, right? There's always going to be that one place that you want to be where there's no infrastructure and you just need a bit of power to run some compute, to keep yourself warm. And it's hard to beat a solar panel for that. But in terms of the massive, massive volumes that humanity needs going forward to power AI, to power robotics, it's going to be nuclear. And it's in even hydrocarbons, right? Most of the world's energy today is hydrocarbons. And if those hydrocarbons become just a transport mechanism for nuclear power, I think you're going to see a world of 99-1. And I think that's going to be a much cheaper way, and it's going to be much more abundant.
Isaiah, as we wrap up this podcast and you get back to work working on a literal nuclear reactor that's in your background, what are you going to do first? Like, seriously, what's next for you? What are your priorities for this week, for this month? Where are you in the arc of what you're trying to build?
Absolutely. The next goal for Valar Atomics is essentially to go rebuild this thing 1-to-1, put uranium in it, and split atoms for the first time. That's all we think about every day. Nothing gets built in the world without it actually getting built, right? One of our big convictions at Valor is that you can only design so much on paper, right? Designing something for 5 years on a piece of paper is going to teach you less than building it in the first year, testing it, building another one, testing it, building another one, testing it. That's what we're doing for the next few years. We're building reactors. We're making them bigger, more powerful, more sophisticated, and we're getting into the practice of building reactors and splitting atoms. That's our entire focus right now. So look out for Ward 1, which will be our first critical nuclear reactor.
And then if you had a message for our listeners are pretty like intellectually curious, high agency people who just always like getting their fingers in the dirt. Any advice for them? How can they support you if they are just like piqued and pilled by your mission, or just any general advice for what they should do if they are just interested in learning more?
Yeah, absolutely. You can follow me on Twitter, Isaiah_P_Taylor. Post some awesome stuff in there all the time. We keep it spicy. You can find Valar Atomics, valaratomics.com. That's VALAR atomics.com. And come visit us. Come check out the reactor.
Where is it? Where is the actual reactor? Where is the facility?
We're here in Los Angeles. We're in Hawthorne, about a mile from SpaceX. We've got great beaches, great surfing, and some of the best engineers in the world creating the future.
I just wanted to let people know to absolutely follow you guys, because that's actually how I found you. I love the theatrics you do around the company, where you guys had this big unveiling event, and I was like, who are these people that are turning a nuclear reactor event into this big thing? And it was you, and it makes the future more exciting. And just wanted to thank you because we need more founders like you trying these hard things, improving our world in this life of atoms, so that the everyday life becomes a lot more exciting. So we're just super, super grateful. Really glad that you joined us today, and excited for other people to hear your mission.
Well, thank you, and I'm glad that you fell for my psyop of the party, which was essentially an exercise to see how many tech bros we could get to show up into a building wearing a suit and tie. And I think that we did. I think that we did quite well. We saw a lot of suits and ties that night on Tech Bro, so it was very successful.
Certainly nerd sniped me. Yeah.
Isaiah, thanks for joining us on Limitless.
Awesome. Thank you so much, guys.